So now I want to take some of the ideas that we had for finite sets and push them towards the case of infinite sets. So let's think about some of the things that we saw for finite sets and try to make them work in an infinite context. So we're moving towards infinity from these finite ideas. So in the previous lecture, we saw that for finite sets A and B, that if we can build an injection from A to B, then it means that A must be smaller than B. Similarly, if we can build a surjection from A to B, then A must be bigger than or equal to B in size. Finally, this means that if we have a bijection, something that's both injective and surjective, then A and B must have the same size. And we use this last one to define the idea of equinumerousness, if you like, for finite sets, but we want to take that idea, namely two sets of the same size, if there's a bijection between them, and extend that idea to all sets, whether they're finite or not. And from this, we can prove, actually quite easily, that this property of equinumerousness, or equinumerous, being equinumerous, is actually well defined, that it behaves as we need it to, as perhaps it should. So, in particular, if we take sets A, B, and C, then being equinumerous is an equivalence relation on sets. So let's let A, B, and C be sets, and then we can show relatively quickly and easily that this property of being equinumerous is reflexive, it's symmetric, and it's transitive. So these ideas coming to us from equivalence relations. And we can prove these quite quickly, basically just using properties of bijections. So let's do that now. So equinumerousness, or being equinumerous, is an equivalence relation. So here's the proof. Well, we have to show that it's reflexive, symmetric, and transitive. And it suffices, in order to do this, just to construct appropriate bijections. So in particular, since the identity function on the set A is a bijection, this automatically tells us, because that map goes from A to A, that A is equinumerous with itself. Then, since if we know that the size of A is equal to the size of B, then we have a bijection from A to B, that's just the definition of equinumerous. Well, we proved previously that if we have a function f that's a bijection, then its inverse exists and is also a bijection. And that inverse takes us from B back to A, and hence we have the symmetric condition being satisfied. Finally, if we know that A is the same size as B, B is the same size as C, then we have bijections from A to B and bijections from B to C. And if we compose those bijections, as we proved previously, the composition G of F takes us from A to C is also a bijection, and hence A is the same size as C. So this bijection definition of equinumerous doesn't depend on the sets being finite. It doesn't depend on us being able to say, hey, this set has some number of elements n, where n is some natural number. It just works on the existence of a bijection. And so this definition works on infinite sets. And that's really why we needed to do this, so that we can escape from the idea that the cardinality is a number, but now we can compare cardinalities by constructing appropriate functions. So here's two examples of this on infinite sets. So let's take the set curly E to be the set of positive even numbers, and the set curly O here to be the set of positive odd numbers. Then these sets have the same size. These sets are equinumerous. And further, the natural numbers have the same size as this set of positive even numbers. This is a bit weird because, well, somehow this is missing half the elements of this. Okay, we only have the even things here, and yet they have the same size. And this is one of our first hints that infinite sets really behave quite differently from finite sets. So let's just see how we can do the first thing. Well, we can go from these positive odd numbers, which are 1, 3, 5, 7, 9, and so forth, to positive even numbers, 2, 4, 6, 8, 10, so on, just by adding 1. And this function is pretty clearly a bijection. It's injective and surjective. Okay, so we're not going to prove that it's a bijection here, but I'm pretty sure you can convince yourself of this quite quickly. Now further, the function, we can construct another function from the natural numbers to these positive even numbers just by multiplying by 2, and that function is also a bijection. And again, you can convince yourself of that fairly quickly. I'm not going to do the details here. But this second result here is quite weird because the set of positive even numbers is a strict subset of the natural numbers. And so what is going on here, even though the even numbers, positive even numbers, there's only half as many, and yet we can construct this bijection. This is a very weird thing that infinite sets do. And we can see this very explicitly, that I can line up here are all my positive integers, all my natural numbers, and here are all the positive even numbers, and I can just line them up. 1, 2, 3, 4, 5, 6. And this list goes on forever, but I can still count things off like this. This is a very weird thing that infinite sets do that finite sets do not do. And this is a consequence of us trying to adapt these ideas for finite sets to the infinite context. So let's underline this. So if we have finite sets with A and B, with A strict subset of B, then if A and B are finite, the pigeonhole principle tells us we cannot construct a bijection. Okay? We can't construct a bijection between these two sets, and we proved this before using the pigeonhole principle. On the other hand, if A and B are infinite, then bijections might be possible. Okay? Then a bijection between these two infinite sets may be possible. We saw this here. The set of positive even numbers has the same size as the set of natural numbers by this bijective function here, namely just multiply everything by 2. Similarly, we can take the set of all squares, all positive squares, so excluding 0 here, that has the same size, and we can construct this just by taking g of n is n squared. In a little bit of work, you can convince yourself that this is injective and surjective. Okay, we have to be careful about domains here because of the injectiveness, but you can see that this is going to work. So one way that we can use this idea to define what an infinite set is, we can use this idea that, that we can, well, let's see, what's two ways that we can do this? Well, a naive idea about what an infinite set is that an infinite set somehow just keeps on going. And this is perhaps what we see when we first encounter the idea of infinity, when we're very, very small and we start understanding what numbers are and we start counting. We ask ourselves, hey, what's the biggest number? We realize that we can just keep going and going and going. We just keep counting and counting and counting and never stop. And this is perhaps our very informal idea of what an infinite set is, namely it's one that just keeps going on and on and on. But we can use this idea about subsets here and the fact that finite sets behave differently for infinite sets to say that a set is infinite if we can construct a bijection from that set to a proper subset of itself. Okay, so that's something that an infinite set definitely does, but a finite set doesn't do. Okay, so this is a slightly more mathematical or more precise definition, more rigorous definition of what an infinite set is compared to a finite set, rather than perhaps this idea that we start with, namely, it's just one that keeps on going and going and going. Now, this second definition here, this formal definition, is due to Dedekind, but I want to use one that's a little bit more precise, that gives a little bit more control over what it means to be infinite. And we'll do a few of these as we go, because we're going to construct different notions of infinite. So here's this first infinity, and perhaps the first infinite sets that we meet is this idea of one that just keeps going and going and going, which is just the natural numbers, the fact that we can keep counting and counting and counting and counting and never stop. And so this is the first infinite set that we encounter, and it's the first infinite set that we're going to define a bit more formally here. So we call a set denumerable if we can construct a bijection from the natural numbers to it, or if you like, between, because if there's a bijection one way, there's a bijection back. So a set's denumerable when there's a bijection with the natural numbers. And of course, this is just saying, hey, the set A has the same size as the set of natural numbers. Okay, so there's a bijection between them. We denote the cardinality of any denumerable set not by this symbol, because that symbol is way too imprecise to its meaning. We're going to make a much more precise notion of what the size of this set is, namely using this Hebrew letter Aleph null. Okay, and this is this notation comes to us from Cantor. So now when a set is finite or denumerable, we say that it's countable. And this is this idea that we can count off the elements, 1, 2, 3, 4, and so forth. Now, in the case of the finite set, we stop. We reach 1, 2, 3, 4, 5, 6, we stop. In the case of an infinite set that is denumerable, because it's in bijection with the natural numbers, we just keep going and going and going. Now, when a set is not countable, we say that it's uncountable. Not very creative notation or terminology, but agree that it works. And there's a few things that come to us from this definition: denumerable, countable, uncountable, that we should think about. Now, first thing is, since if we have a bijection this way, then we have a bijection back. That's just because any bijection has a bijective inverse. We also know from the things that we did just a slide or two ago, that the set of the positive even numbers, positive odd numbers, and the squares, positive squares, are all denumerable. And so, because a set is countable when it's denumerable or finite, we know all of these sets are countable. Now, there's some obvious questions to ask here. So first one is, if we look at all subsets of the natural numbers, are they all countable? Are they either finite or the same size as the set of natural numbers? Or is there some infinity in between the two? So is there some infinity that's bigger than finite but smaller than the natural numbers? And then we can ask, are all supersets of the natural numbers denumerable? So if we look at supersets of the natural numbers, so all integers, the rationals, the reals, are these all the same size? Are they all the same sort of infinity as the natural numbers? And then the last thing is, well, we've defined this idea of something not being finite or denumerable, namely being uncountable. Do any uncountable sets exist? This is actually quite a controversial result when it was actually shown. So we have some questions that we want to answer before we're done in this course. So let's stop there.